Okay, guys, I think we gave it enough time for people to join. So good evening and welcome to our Natural Intelligence fourth data webinar out of the mini series of 5 meetings webinars that we set. So we're at the end of the streak. A couple of words before we begin about natural intelligence. We are a global leader in multi-vertical online comparison marketplaces, and our matching technologies enables consumers make confident purchasing decisions while helping brands grow their business. In other words, we're helping people like you and me select quality services online. And for that, we're building comparison sites. And we have a very cool vision. We want to build the comparison site for everything. Imagine a single place where you can go and get comparison of any kind of services you'd like in hundreds and thousands of verticals, of areas of services. Natural is a rather young company. We're about 10 years old, 400 employees, and we've built, in order to achieve this goal, we've built a couple of platforms, and we're running millions of users today. And our, let's call it, technology stack is cloud-based first. We're Amazon from day one, Amazon Cloud. We've built our web infrastructure and platform using Node and Mongo and a bunch of other technologies. And our, let's call it, funnel is unique in a way that a lot of our traffic comes from marketing campaigns, comes to our sites, people come to our sites, get data they need, and then go to our partners. We have about 1,000 partners today. And we want to know what were these users, what they did prior to being on our sites and after they being on the site, because they actually purchased. And we want to be able to look at this pretty complex funnel that starts outside our systems and ends outside our systems, and analyze it. We're practically a very data-driven company. And in order to do that, we actually built a data platform that is based on a couple of state-of-the-art technologies, including S3 as our data store, Spark and Airflow and Glue. And we've been discussing all of these technologies and problems and issues, challenges of building such a data platform in the last webinars. And today we got to the webinar that we'll be discussing how to make our data platform, Data-Lake, production grade in order to build quality data, machine learning up to the top of it. And this is the 4th installment, and Aviem, our data tech lead, is gonna run this webinar, this session. So Aviem, go ahead and have one more thing before we start, sorry. 2 things actually. One, next week, Monday, we're gonna have the final webinar. I'm gonna discuss more complex data ingestion with Daniel, another tech lead in the company. And during this session, please feel free to use the Q&A button at the bottom, ask questions. If it's gonna be something I can answer immediately typing, I'll answer it. And anyway, we're gonna do a follow-up after the session and answer any question you'd have, as time permits. So start thinking about the questions, write them down, and this is going to be the way where we're going to answer them after the session. So Aviem, go for it.
Well, I'm Aviem, and what we're going to talk about today is production-grade data and ML applications and ETLs over data lake on AWS, which is a very long sentence. So let's try to break it down. First of all, who am I? My name is Aviem. I'm a data tech lead at Natural Intelligence. an open source enthusiast. I am a committer in the Apache Beam project and a member of the committee which manages that project. And in my spare time, I like to play Magic the Gathering, the card game. What are we going to be talking about today? So we're talking about productionization of data and ML applications and ETLs. And we want to describe our data platform, and we'll do this in 3 parts. So first we'll define what a platform is, then we'll show NI's data and ML platform. And in the end, we'll have a short discussion about open source at NI. So what is a platform? A platform enables developers to deploy production-grade applications while focusing on their problem's domain. So what does this mean? This means we have hired talented people in different problem spaces, and we want them to focus on that problem space. We don't want them to worry about anything non-functional, from getting their code to production. And this platform, we expect from it higher quality. We expect from it higher developers' quality of life, since they will only focus on their domain. We expect less faults, higher availability, and developers who focus on their own domain and have their software development lifecycle and all that is non-functional provided to them by the platform. So we've mentioned the software development lifecycle. This is the heart of the platform for the user. The user in this case being an application developer who's focused on their business domain. They develop on their IDE, push their code to source control, where it is built for them in a CI and CD service, and deployed to runtime to production servers. When running in runtime, we output logs and metrics, which we collect in a monitoring and alerting layer, which then can be accessed as alerts and dashboards to the developer, and the cycle repeats itself. Okay, so that's pretty general. How is this implemented in NI's data and ML platform? So in our case, our users are engineers, data scientists, analysts who want to focus on their business domain and what they know how to do. So they develop each in their appropriate IDE, push code to GitHub, which we use as source control. Then their projects are built in Jenkins, which is our CI service, and deployed to our runtime, which runs on Kubernetes, Apache Airflow, and Amazon EMR, ElasticMapReduce. And then we collect logs and metrics in several different services. There's Amazon's CloudWatch. We have our InfluxDB for our applicative metrics, and Grafana can read from that InfluxDB. And we have Datadog and PagerDuty for the alerting front end that the user interacts with, the user being the application developer in this case. Okay, so they develop apps which then form together a rather complicated data and ML flow, which we won't go into too deeply. But basically, we have raw data from different data stores, which is then processed by data ETLs, which output processed data. Then our applications, for example, data science applications, can run their code on that data, extracting features, training, storing their trained model in a model store. And we have online inference for HTTP APIs, and batch inference for large inference jobs. And this whole thing forms our flow. Now, what does the developer see? How do they interact with this flow? How do they interact with the SDLC? Well, we provide to them an API which they can use when they develop. And this API is currently YAML API. And in there, they define what we like to refer to as a data pipeline. A data pipeline can be made up of different data processing tasks and usually is run on some sort of schedule. For example, once a day. So this is an example of one such YAML. So for example, I have a pipeline, I name it my pipeline, and I give it a start date and a timeout minutes. There also should be a schedule here. It's missing, but there should be schedule in cron syntax for when we want this pipeline to run. And we can define a metrics backend. So all our basic metrics that we collect for our applications go to CloudWatch. And then we define what resources we want for our pipeline. So we say we want an EMR cluster. It doesn't have to be persistent to save on expenses. We launch ephemeral clusters, which we terminate when the job is over. And some configurations about this cluster, how big it is, what version it has, and so forth. And then we define a task. So a task, we have several types of tasks which we support in our platform. One of them is a Spark task. Take my jar and run it for me on EMR. And I can give overrides for specific environments, prod, staging, different configurations, and everything is overridable per environment. So this is an example of a data application. Another application, which is rather popular at NI, is an SQL application. So if I can describe my ETL as SQL and don't require any coding, then I can develop a whole ETL just by making this YAML file. So let's say I'm a business analyst and I want to create a persistent view over some large table in the data lake. I don't want to wait for engineers to develop this for me. Don't want to be stuck in some backlog somewhere. So just register one of these ETLs, and I've created my own ETL via SQL. So everything is similar to before, except now we have a task with type SQL. We write some query of where to generate the data from, what partition columns we want to have in our output data, the name of the table we want, output path, and this will also update the metastore, being glue in our case. And then we have ML applications, which are slightly different than data applications that we've seen before. So here's schedule, if you wondered what that looks like. So a data ML application usually runs Python code in our case. So we have a task type called Python, which I provide to source relative to this file's location. And the platform will compile my code and build a Docker image that runs my code without me, the data scientist, needing to know anything about Docker, Kubernetes, deployments, any of this. I just need to configure this. Now, currently, we have a YAML API, but we want to expand on this in the future and have users of this platform maybe access it in a different way, like in a web service, which they have wizards within. They can create pipelines and don't need to fill out a sort of YAML manually. That's the future for us. Currently, we work with YAMLs. So this Python task can set environment variables. We can input data into the Python task. So for example, we can have static inputs, and the command I want to run in this task is Python hello world. We have parallelism. So if I mention number of executors, then I will create that many instances of this task running on parallel executors using Airflow in Kubernetes. And another input I can have is an input that is an output of a previous task in the pipeline. So I can say input type task and my static input task. So I want the output of this task to be the input for this task. And this allows us to create these sort of flows of data science with inputs and outputs between the different tasks. And something we haven't seen before in our YAML is another type of entity called a service. So in addition to tasks, which run in a pipeline, in a section called pipelines, under services, I can create services, which also have different types. For example, here is a Python server, which we want to use to serve the code in this repository as a service. So I just need to say my Python server, type Python server, what the name of the image I want, and where is the source code that the server will access your code. So again, relative to this YAML's location. And you can define endpoints for your service. For example, my endpoint 1 will go to my server and run method my server. So package my server, so Python file within the source. And I will run a specific method, in this case, my server. The name of the package is my server. So my server.myserver, and the name of the function, my endpoint1 func. So this will launch a Flask HTTP server running on Kubernetes with multiple replicas. And it will serve an endpoint called my endpoint1, which will run the user's code found in this function in their code. So all of this we were able to create simply by filling out a YAML and pointing it to where my code is relative to that YAML file. And we can also mix and match and do everything together. So a data and ML application which does all the things that we've seen. So an SQL ETL followed by the same Python task we saw, followed by a Python server to be running persistently. So for example, we can do some transformations on data by an ETL that I can describe with SQL as a data scientist. And I can then run Python code to train a model every interval, so once a day, for example. And that model will be available for the runtime server, which serves that model's inference as an HTTP endpoint. All of this I've done as a data scientist by filling out a YAML. I don't need to know anything else other than that. So where do these YAMLs run? What does our runtime look like? So our data lake is files on S3. And for data catalog, we have AWS's Glue as our data catalog. Other services we have in our platform in the data catalog layer. And we have event ingestion, which creates tables of event data available on the data lake. And we have NI metastore utilities, so polyglot utilities for accessing that metastore. Since we have applications in different languages, Scala, Java, Python, Node, we have to create these utilities in a polyglot fashion. And now we get to the vertical layers. Those were the vertical layers of our platform, but we also have horizontal layers to the platform. Our platform is built in layers, layered upon each other. So our user created an app, as we said before, and then they hit the CI/CD layer. They push their code to GitHub, and based on that YAML that they defined, Jenkins runs what we call data infra pipeline, which results in a running data pipeline in production. So where do the applications themselves run, the ones that we compile in the CI/CD layer? Well, we have Airflow for scheduled types of pipelines, and Kubernetes to run both the Python code in that pipelines and any services that we run, Python servers, for example. And we have Amazon's EMR for data applications, for example, Spark applications, which we create a lot of. Then we have a monitoring layer. We need to monitor all of these applications if we want to be production grade. So again, we want the user not to have to deal with this sort of thing, but to have it happen automatically. So we use Grafana and InfluxDB and Datadog and CloudWatch as we defined before. And we have our layer of code called an eye monitoring util, which the purpose of this is first to provide polyglot basic and applicative metrics that you can send from your application. So basic metrics are metrics that we send automatically for apps running on the platform. And that's app started, apps finished successfully, app finished in a failure state, and duration of the app's run. Those are basic metrics we send for our pipelines. And for our services, we use Datadog's APM to monitor our servers. So that was a very simple implementation of that. Another thing we want is to define alerts automatically and have new application onboarding be simple. Again, we want people to stick to their own domain. We don't want them to have to configure alerts on their metrics and so forth. So for those basic metrics that we collect for every application, we have a layer to create alerts automatically to ease developers' time to market, time to hit production by defining these things automatically. And applicative metrics, we provide different utilities in different languages for them to send applicative metrics, which we store in InfluxDB, because CloudWatch and Datadog are shared resource for the company, and we can't overload it with data because there are limits, because there are services outside the company. And InfluxDB and Grafana are our own, which run on our Kubernetes cluster, and here we store our larger data. So applicative metrics, where the users can generate metrics and send them as the application runs. Another layer we have on top of this is a utility layer. We have some common utilities like a checkpointing mechanism for applications which run on a schedule and rely on a checkpoint to know what they need to do when they run, what data they need to read, for example. We have an integration with Amazon's SSM to hold sensitive data, credentials for services, stuff like that. And we have a properties utility to allow users to configure properties, as we saw in the YAML file, per environment, and to have these injected to their running apps. We have Spark utilities, so distributed applicative metrics. So we wrote a layer that the users can create metrics, which will be calculated on all the executors in the Spark cluster. And when the application ends, it will result in these calculated metrics without adding extra time for that application to terminate. So we try to make it as performant as possible. We have a layer of validation. We have a layer of testing, which allows users to create unit tests and integration tests, which run on actual clusters. And we have Airflow utilities. And as we were developing our Airflow utilities, which allow us to implement that YAML we saw, the pipelines defined on Airflow, we contributed operators that we have developed back to the Airflow project itself. And we're starting to be more and more involved in that project since we use it exclusively for this platform. On top of that, we have a layer of generic services. So when a problem arises again and again and again, we can create a generic solution to that problem. For example, the SQL ETL we saw before, which enables both engineers, analysts, data scientists to create ETLs just by configuring SQL. We have data science batch and real-time inference layers, as we saw in the YAML file. And any use case that repeats itself enough times, the developers and the company themselves contribute back new types of services and new types of tasks and services that we saw in the YAML. So say they did a lot of ETLs that copied data from our data lake to JDBC databases for online applications. So that use case repeated enough that one of the engineers in the company created a task type specifically for this, copying data lake to JDBC servers, JDBC database. And they can extend this platform to add more task types and more service types as we proceed developing it. And our last layer is the highest layer of the API, which is the YAMLs that we saw. That's what we call our data pipeline API. And we have data app archetypes. So if you're creating a Spark app, for example, so with the push of a button, you get a new repository with a Spark app skeleton and with tests and examples. And our goal is to have different type of app archetypes for apps that we see that repeat themselves. So not just ones that we can define as a configuration, but ones that still require code. I want to give them a leg up and reduce the time to market by creating that app skeleton. And that's basically it for our layered architecture of this platform. So I want to talk a little bit about open source at NI. So as we mentioned, we've started contributing to the Apache Airflow project, which we use for our platform. And we generally try to have our developers embrace open source and make their own contributions to open source projects, especially those tied to what they're doing at NI. And in addition to this, the platform that we just saw, we are in the late stages of starting incubating in the Apache incubator for a new Apache project for our data platform. Our code is open source, so you can find it on GitHub under Natural Intelligence. And once the project starts incubating, it will be available in Apache's GitHub. The name is not yet set on our GitHub. It is called Rainbow, but there are some legalities issues with the name. Nothing we need to get into, but we are looking for a final name so we can start incubating in the Apache incubator. And once that happens, we urge people in the community, you, to also contribute to that project. And we want to push it forward by having more eyes on it and more people from around the globe contribute to it. And we have backers from within the Apache incubator, which believe in this project and are pushing it themselves. And we already have outside contributors from our company. We have consultants in the data area, in the data world, also contributing to this project from outside the company. And we want to invite more and more companies. So once we start incubating, the idea is to spread the word. And for those who want to ask the question why we created this new project, why did we do this from scratch? Why not use something that already exists? So we did our comparison of what was available in the market and the open source solutions. And we didn't find anything which hit all our flags. This research that we did will also be available on GitHub in our project once we've converted it to something we can put online. We couldn't find something that served our purposes. We tried Amazon's SageMaker service, but did not tick all our requirements. So we ended up defining this API for a data platform, which can run both our data applications and our data science ML pipelines and serving at real time, which are real-time production servers make API calls to these services. So it's part of our front line of services. And we were able to empower data sciences to create data scientists to create these sort of production applications without having to worry about all this non-functional stuff and be able to focus on what they do best, which is training models, creating new data science solutions. and not having to deal with deployments and monitoring and all that sort of stuff. So let's sum up what we talked about here today. We discussed in a broader sense what a platform is, and then we showed what NI's data platform looks like, and we had a small discussion about open source. So why do you want to have a platform? Why would you want to contribute to this project? Well, the idea of what I get back from the platform, as we mentioned before, we have higher quality, higher developer quality of life, maximize the use of your engineers' time, and have them only deal with problems in their domain. We have less faults, higher availability, and the developers have SDLC and non-functional provided to them, so they can do what they do best. And that's it from me. If you have any questions, you can post them in the Q&A area, and Amichai and I will try to answer all of them if we can. And that's it, Amichai.
Yep. So we already have a couple of questions. So let's start with the easy one. Is this the one called Rainbow? You want to take that, Avir?
Yeah, so currently it's called Rainbow on our GitHub, but there are problems with that name and trademarks, so we're finding a final name with the Apache incubator, and once we lock down that name, we'll start incubating if all goes well. Have you tried Upsolver by any chance, Amichai? Can you answer to that?
No, I actually have no idea. Never heard of it.
No.
Sorry. But we would like to hear a little bit more about that. Let's take the first one, Mikhail.
Yeah.
Am I saying the name right? I'm sorry. What about resource management for machine learning, related tasks, limits, requests? Do the scientists need to configure the system? And we have experience with OOMs and okay. VM?
So yeah, they configure it in that same YAML. They say what the max memory, max CPU, and requested memory, requested CPU that they want. And we work with DevOps to figure out if we have any applications which take more resources than they need. So that feedback comes back really quickly. And again, without having the users, mostly data scientists in this case, have to worry about that sort of thing. So simplify it as much as we can so that YAML defines everything that they need, including how many CPUs and how many memory and how many replicas of their service they want and so forth.
Okay. Guys, anybody else want to ask a question? This is the time. Give you another minute for that. Okay. Did you have any intermediate stages along the way? Was it a gradual process, or you performed the jump right away? Great question.
Yeah, so it wasn't an immediate process. We started with our platform for data applications, which started with the utilities and what a skeleton of a project looks like and the deployment of that. And we started with auto-generated Airflow DAGs from a template for each of these applications. So still, data engineers did not have to deal with all that side. They just have to fill out basically a smaller version of the YAML we just saw, and DAG would be generated. And when they when their code was built on Jenkins, then a DAG would also be built and deployed to Airflow accordingly. And after that, we tried to generalize the problem of a data platform to also include data science applications. which also need to run, which also we don't want to have engineering sort of engineering resources on every team that has data scientists. We want them to be able, with a self-service approach, be able to create data pipelines that train their models and services which serve inference of those models for our production services. And that is when we try to generalize these problems and created the API that we looked at before. And that was after we did research if we can't use something that already exists to solve our problems, mostly in data science, because for data applications, there are several platforms. But our focus was on the features required for machine learning applications and services without the need for extra engineering resources other than the ones that already existed to create our data platform as it evolved.
Yeah. I can add another, let's say, short reference to the fact that once we actually built it, we were focused on the machine learning part, but it actually became very quickly very useful for our own ETL processes. So the same system, since you run SQLs and Spark jobs on it, is actually used to speed up our time to market in standard ETLs that were, business were requesting. So that was a win also. And maybe Avim, you would like to discuss the reason that we didn't go with something like SageMaker, for instance, because we've checked SageMaker, right?
Yeah, we have. So none of them looked holistically end-to-end that we want basically this business logic to be in production without having to go through many steps along the way. And for the business logic, which the specific personnel, for example, data scientists, translate that business logic into their code, we want the next step for that to be as minimal as needed to get to production. And right now that's a YAML file that they have to define. In the future, we want to make it even simpler. So the idea is simplicity, so you can maximize the use of your employees and have them focus on what they do best. And that generally gives them a higher quality of life as well.
Sure. So do we have a data warehouse as well as, in addition to a data lake?
Yeah.
The answer is yes. But we try to focus the data lake is the core, is the source of truth, if you will. And we use data warehouse, we use Redshift on top of it in order to make our life easier for faster querying and maybe some use cases where you need these, the advanced capabilities of a data warehouse. But from my perspective, as a data platform architect, the data warehouse part is a part of the data lake. Okay, it's a way for me to access the data and use it so we can actually are accessing this data as part of what we're just discussing. So I can access data using Spark and in S3, and I can also access data in Redshift, and I can do any kind of a combination I need to do with it. So languages, Python, Scala, Java, right, Avim? Do we have anything else?
Scala, Java for data, yeah. So Spark applications usually in Scala, and data science applications usually in Python. And our data platform itself is in Scala, Java, and Python. The open source project is primarily Python right now, but as models are added to it, those models will use the appropriate language for them. For example, a web interface would use a relevant language for web interfaces.
So what is a task?
A task. So our pipelines are broken down to two separate parts. There's pipelines and services. And you can define a pipeline which, a YAML which defines several pipelines and several services under one holistic application, which takes care of all of those. So we have several task types. We have Spark task type to run a Spark application, SQL task type to run an SQL application, Python type to run Python code as a Docker image on Kubernetes, and more custom task types that our engineers keep adding as their use cases arise. And our services, currently we only have one service type, which is a Python server, but if the need arises in the future, then we'll allow for other types of languages, Java, Node, whatever people want to write in our company, and we support.
Okay, so is the data warehouse near real time, or is it with lag? So it depends. What do you mean? We're not updating the data warehouse with streaming, okay? We're running a bunch of ETLs, and then we upload the data at the end of those processes, some of it into the data warehouse. So it's not real time in that manner. We do access it with and do speedy queries on it, but again, those queries are not for, it's for big, let's call it multiple aggregative queries. I'm not sure if you know Redshift, but it's a, let's call it a columnar database. So it's using resources and it's doing very, very fast querying in parallel to a lot of data. And this is where it shines over a regular, let's call it S3-based Spark, because it's going to take us hundreds of milliseconds to do a very, very big query on it. When we run it with Spark, it could take minutes. So this is where it shines, but it's not like a real-time database, definitely not for transactions. Do you use special tool for the ETLs or just programming?
We had a legacy system using a software as a service ETL, and we migrated from that to exclusively using the data platform with either Spark applications or SQL applications defined in our YAML configuration for the platform. So right now we don't use any extra tools for ETLs.
Yeah. So does the platform enable data scientists to debug their code against a remote cluster while running it on their own laptop, IDE, remote? Yeah, I can see where it's going, a VM.
No, right now we do not support this. However, they can run their code on notebooks, on production servers, and be able to access production data as they do their research. But they don't have any live debugging other than that for the running applications or pipelines or servers. But as the platform evolves, if such needs arise and we have contributors which want to contribute it, then we might develop something like that as well.
Yeah, it's a cool feature we find very interesting. We discussed it a little bit. It's a little bit down the stretch for us, you know. As we discussed before, it was stages of building it into maturity. This is another step of maturity. I'm pretty sure we're going to get to it. And again, if anybody wants to join this project and this open source project and contribute, there's a bunch of very, very cool stuff we still need to do in it. It's very, very powerful, but there's still a lot to do. So I think we're about done, guys. Any last questions, or we can call it a night? I'm gonna give you a few more seconds. Okay. So thank you, OVM. It was great. Thank you guys for joining us from all over the world. And I hope we see all of you next week on Monday. We're gonna have the final webinar. And as I said before, and I actually wrote it as an answer, all of our webinars are recorded, and they're all available in the Natural Intelligence YouTube channel. And I also listed the URLs that are already for the direct videos. You can find them easily. So take a look. There's a bunch of this session today is sitting on top of a bunch of other sessions that are building it up, so it would be a little bit even more comprehensible about the entire structure of what we did and how we migrated. There's a lot of interesting questions about it. Pretty sure you're going to find it interesting. And thank you very much, guys, and have a great evening.